Majority of what we talk about today is review with complex numbers. Complex numbers, you were first introduced to them last year in Algebra 2. So if you've taken Algebra 3, you've seen them 2 times before. We need to review them because from here on out, we're going to encounter some complex number answers, so we want to know how to work with them. Does anybody recall what the standard form for a complex number looks like? When I talk about complex numbers, look at my hierarchy down here. You might recall them as the imaginary numbers. Does that help you recall any standard form? It has 2 parts, every complex number. A plus bi. Remember that guy? Okay, you got a real part A, you've got an imaginary part bi, and those are complex numbers. What does I represent? It's the imaginary unit. And what is it equal to? The square root of -1. So you should have had some discussions like, what number would multiply, can you take your earbuds out? What number would multiply by itself to give you -1? No number, right? A negative times a negative is always a positive, and a positive times a positive is also a positive. So we introduced I as the imaginary unit. It's equal to the square root of -1. But mathematicians don't really write square roots of -1s. They always replace it with i's. Okay, so just to kind of clarify from last year, prior to that introduction of the imaginary unit, you thought all the numbers that existed were real numbers, and there was one big giant box for real numbers, and you could break them up into rational and irrational, and you had subsets, integers, whole numbers, etc. Okay, but then we said, oh, well, there is this number that's not real, but it exists, I, and so we made your box bigger. So the biggest box you have of numbers is the complex numbers box, and every complex number can be broken up into real numbers or imaginary numbers. So I just want to clarify that for everybody, that complex real numbers are actually complex. They're all just in the form a plus 0i. When we're teaching you to count 1, 2, 3, you're not yet at the level where we're going to teach you 1 plus 0i, 2 plus 0i, 3 plus 0i. But know that all real numbers are actually complex. Okay, they just have no imaginary part. Imaginary numbers are those where we have a plus bi, where b is not equal to 0. And then if you're really interested in the study of subsets of numbers, just a quick reminder that those can be broken down further. So we have like the rational and the irrational. Rationals we can break up into integers, which there's a subset, which is whole numbers, and you can even do counting numbers if you want. Imaginary numbers does have a subset called pure imaginary, meaning it's in the form a plus bi, but it has no real part, right? It's all imaginary. So pure imaginaries are of the form 0 plus bi. So if you ever see something like 5i or -2i, that's a pure imaginary number. Okay, so you studied, drop something there, Aiden. You studied complex numbers last year, and you did some operations with complex numbers. I am positive that all students entering the room have done add, subtract, and multiply. So you're actually going to practice those on your own here for about 10 minutes. Around the room, there's blue and like salmon-colored cards. They're labeled, see the big letter at the bottom, A, B, C, D, and E, so there are 5 of them. There's like multiples of each. I do have a C up here on my cart in white. But now's your chance. You're going to get up. You're going to move around. There's a little blurb at the top if you're having trouble remembering what to do. Just like a little hint about how to add, subtract, or multiply. When you get it done, you can flip it up. There is an answer there for you to check to make sure that you have correct answers in your notes. Side note, make sure all of your final answers are of the form A plus BI. Put the real part first, the imaginary part second. Okay. And I'll give you 10 minutes to do that. We'll come together and we'll talk about division. Because not all classes, like Algebra 2, I don't know that they divide complex numbers. It's not in your new book. And we'll also talk about the cycles of I. So go ahead, get up out of your seat. Now is your chance. All day long, you're sitting in your desk. Get up, walk around. You can go in any order. You can work with a friend. You can work alone. Do a problem. Ask a question. See me for help. You've got 10 minutes. So 11:15. I'm going to write that down so I don't forget. Get that blood flowing. Move around the room. Any problem, you don't have to go in alphabetical order. There's just 5 to do. If you disagree with an answer on the back of a card, let me know. Yeah, so there's doubles. So there's like 2 A's. I think 1 blue A. Okay, but there's so you just want to try to do A, B, C, D. Don't forget to check your answer so you know you did it correctly. And make sure your answer is in the standard form. I will say one thing there, that doesn't look like standard form because you have an I squared. So do you remember anything from last year about squared? Think about this. I is the square root of negative 1. So you replace it with negative 1 and then you get 1 back. Good. Did it work out?
Oh, wait.
Oh, you brought it up. I got it. We're like, line area. Okay, so like 4i times negative 2 is negative 8i, right? And 4i times negative 3i is negative 12i squared. Yeah.
Oh, it should be 12. Yeah, I just did multiple.
Oh, you using do you remember anything about the square? So if I
Yeah.
make a substitution, then we can get back to what you supposed to be at. Yeah, I would just combine the like terms, negative 8i minus 3i. And then like, did you already in your head do like negative, like this is a positive 4i squared, so then it's a negative 4? Okay, just make sure.
We know.
or two. I tried to do it real fast. So you have some examples.
It's
Like you can see my
Cube of a rock.
You broke it up.
I just worry about you.
So
Oh wait, did you do in your head like 12? They turn into I squared. Yes, so it will be a negative. Right? So then if you're doing 4 times negative 3, that's negative 12. And I guess we're going to you know how to do yours for now. Okay? Oh, okay. Yeah, is that the answer to E?
I just didn't change the last
Oh,
one.
okay.
I finished.
Okay, just making sure. Amanda, how they go for you? Okay, any questions? Yes, how they go?
Good.
Where are they?
Oh,
You have put any examples in your notebook?
was.
Okay, on this end has got to show me all your work, right? All right. Take a minute if you're kind of finishing one up or you need to check one more answer, go ahead and do that. I'm just going to kind of debrief here. You know, if you're adding and subtracting complex numbers, what are you basically doing? Adding and subtracting, which is combining like terms, right? I mean, that's what you're doing. You're grouping real parts with other real parts and imaginary parts with other imaginary parts. I'll always put out my warning about subtraction because if you're subtracting a complex number, it might have 2 parts, like an a plus bi. So you got to subtract both of those. It's minus a minus the bi. Distribute the negative, change it to adding the opposite. Don't forget to subtract both parts of a complex number. Multiplication is just like multiplying or foiling, like with variables. Treat I like a variable until you get your answer. What if your answer has I squared in it? I squared is equal to negative 1. If I is the square root of negative 1, then I squared is negative 1. You can make that substitution. It changes the sign of that numbered coefficient, and then you can add that with your other real parts. So your answers, reminder, and check your answers right now. They should always look like a plus bi. You should never have an I squared, an I cubed, or any other value in your answer. You should always have your real part first and your imaginary part second. Okay, we're going to talk about division. And the weird thing about dividing complex numbers is you're not actually dividing them like we think about division. So there's an old school math rule that says you're not allowed to put radicals or leave radicals in your denominator. You always have to rationalize your denominators. Well, if you leave I in your denominator, it's like leaving a square root of negative 1 down there. So the rule kind of extends. We can think about it and we say no i's in the denominator. So to get I out of the denominator, we're going to do this. Multiply the numerator and the denominator by the complex conjugate of the denominator. So really a division problem in complex numbers actually is more like multiplication. It's multiplying in the numerator, multiplying in the denominator so that you multiply by what we call the well-chosen 1, a value of 1 that will give us an equivalent fraction. Now I'm going to talk about complex conjugate here in just a minute, okay, but just make sure that you have this note down. If you know this little piece to get I out of the denominator, you're golden for division of complex numbers. This is the one operation students usually have the hardest time with. Okay, so what is a complex conjugate? Well, it's just like a regular conjugate other than the fact that it's made up of complex numbers. So a regular conjugate is one where the sign changes in between two terms. If they're complex numbers, we'll have an a plus bi and an a minus bi. Note that in complex conjugates, you're never changing the sign of a, the real part. You're only changing the sign of the coefficient for b, the imaginary part. Okay. I'm going to multiply these two complex conjugates together one time. This is good for some of us to kind of stretch into like patterns that we notice. This is a common pattern that many mathematicians will use as like a shortcut. If you don't really like the shortcuts, the memorization, the patterns pieces, then you have to do the math work and multiply it out every time. But I'm going to multiply it once here for you. A plus bi times its conjugate a minus bi. Who cares what the numbers are? What will we get? A times a is a squared. A times negative bi is negative abi. A times bi is plus abi. You gotta be careful on the last one. Bi times negative bi, that's a positive times negative, so it's a negative. B times b is b squared, and I times I is I squared. So it's a b squared, I squared term. Okay, well, why are we going to multiply by the conjugate of the denominator? Because we don't want to have i's in the denominator anymore. And what happens to these two I terms? Gone. Conjugates always get rid of the middle terms. That's good. So I'm left with a squared minus b squared times I squared. But you guys just told me I squared was negative 1. So we're going to have a squared plus b squared. So every single time you multiply complex conjugates, it does not matter what the numbers are. If you did a squared plus b squared, that's what it is. Okay, so if you want to use that when you're doing division of complex numbers, I'm fine with that. Notice that there's no I in that, so you're going to have a real number in your denominator now. Okay. Let's do an example of division, and then we'll talk about cycles of I. So we'll do this example. 2 plus 3i over 4 minus 2i. Okay. Remember, do some practice with this so you don't get confused. You're not really dividing. You're just looking at that and saying, no i's can be left in my denominator. So we're going to focus on the denominator. 4 minus 2i. To get rid of I, we're going to multiply by its complex conjugate. Addie, can you tell me what the complex conjugate of 4 minus 2i would be?
Oh, minus?
Change. 4 plus
2i?
Yep. Put you on the spot, right? Okay. You are going to get rid of I in the denominator. You are always going to multiply by the conjugate of the denominator. It is not the same as the denominator. It is changed signs of the second term. So if I multiply the denominator of my fraction by 4 plus 2i, I have to multiply the numerator of my fraction by 4 plus 2i. And this is where I'm talking about really you're not dividing. Now the rest of your problem is multiplication. You got multiplying the top and maybe a multiplying the bottom. So go ahead and FOIL those out. See if you can get the same answer that I'll get. FOIL, FOIL. If you want to use my trick from multiplying complex conjugates, you can give that a go. So it will be minus 4i squared, but I squared will change to a plus. So the I squared always changes the sign. That'll be coefficient. Okay. Here's what I get when I FOIL. 8 plus 4i plus 12i plus 6i squared in my numerator. So check your 4 terms. I can combine the i's, so this is going to be 16i. And I'll have 8 plus 16i plus 6 times negative 1. Well, that's 8 minus 6. So do you agree 2 plus 16i in my numerator? Are we okay with that? Okay, and then in your denominator, I'm going to FOIL this one out first. So do first outside, inside, last. I get 16 plus 8i minus 8i. And then careful on your last terms, watch your sign there. That's going to be 4 minus I squared. But remember, our whole goal here is I should disappear. So plus 8i minus 8i, that's gone. That's good. And then this turns out to be 16 minus 4 times negative 1, which of course is 16 plus 4, or 20. Now remember, you could have used how I did that with the a plus bi and a minus bi on the last one. If I'm multiplying 2 conjugates, it will always be a squared plus b squared. So it would be 4 squared plus 2 squared, 16 plus 4 is 20. I would have got that answer without having to FOIL it out. So if you like that, that's a shortcut you can use. Now, there's one final step. To write it in standard form, remember we want a plus bi. We want to have individual coefficients. So if you have a number in your denominator, you're going to divide each term by that value. So 2 over 20, what's my a? 2 over 20? 1/10. And then 16 over 20 is going to reduce to be 4/5. So this way, I have a real coefficient of 1/10 and an imaginary coefficient of 4/5 that I could identify as my A and B. So you always break it up. Okay. Any questions about dividing your complex numbers? Okay, last thing we want to talk about, cycles of I. Okay, some classes may or may not have discussed cycles of I in Algebra 2 or Algebra 3. So we'll kind of start fresh. I'm going to start with like the lowest exponent I to the 0. What do you get when you raise I to the 0?
1.
1. That's the 0 exponent property. Anything raised to 0 is equal to 1. Okay. Now, we said on our first slide that I was the square root of negative 1, right? But when we do the powers of I, if we have I to the first, we're just going to call it I, right? And then we already did I squared. We know I squared is negative 1. So probably the one part of the cycles of I that you need to review is going to be your I cubed. Would you agree with this statement? I cubed is really I squared times I. So then you would add your exponents. So make a substitution. What's I squared? Negative 1 times I, which is just negative I. So I to the 0 is 1. I to the first is I. I squared is negative 1. And I to the third is negative I. Now, I to the fourth. I'm going to break up I to the fourth like I did I cubed, but I'm going to say, isn't I to the fourth I squared times I squared? Which is negative 1 times negative 1, which is just 1. So I to the 0 is equal to 1, which is the same as I to the fourth. So if I add another I, then I'm just going to go down this cycle each time. Okay, so this is going to be I to the 5th, I to the 6th, and I to the 7th. And then once I get around, I just go right back up. I to the 8th, I to the 9th, I to the 10th, and I to the 11th. Okay, now there's a pattern here that we can use to help us evaluate cycles of I fast. Okay, it's usually easiest to spot in the first one, I to the 0. Look at all those exponents. 0, 4, 8. How are those numbers related? 0, 4, 8. Next one would be 12. What's that, Austin? They're all what?
They're all multiples of each other?
They're all multiples of 4, yes. Okay. If you're a multiple of 4 and I divide you by 4, what is your remainder? 4 divided by 4, 8 divided by 4, 12 divided by 4, remainder 0. Where do you see 0? In the exponent. Okay. Okay. Look at these numbers. 1, 5, 9, 13. If I divide those numbers by 4, 5 divided by 4, remainder is 1. 9 divided by 4, remainder is 1. 13 divided by 4, remainder is 1. Where do we see 1? In the exponent. Is this making sense? Okay, so these are all remainders 2 and these are all remainder 3. So if you divide your exponent and its remainder is 3, it is negative 1 or negative I. Okay, if you divide your exponent and it is 1, then it is I to the first or I. So let me show you how we can use this. Okay, here's a quick and easy example. 2I cubed plus I squared. Well, those are the basic cycles of I, right? You need to know I cubed is negative I, so you can make that substitution. So that's 2 times negative I. And then I squared is negative 1. This is negative 1 minus 2I. What if I throw in some more interesting exponents? We don't want to go around and around. We're just going to use division. There's 4 cycles of I. Divide by 4. If you divide 25 by 4, what's your remainder? 1. goes in 6 times for 24 with a remainder of 1. So this is the same as 5i to the first. Okay, if you divide 74 by 4, what's your remainder? 74 by 2? 74 by 4? 2 is your remainder, right? 18 goes into 72 4 times, so there's 2 left over, so this is 3i squared. Make the substitutions from the cycle of I. This is 5i plus 3 times negative 1, which of course is negative 3 plus 5i. So you're using the patterns of cycles of I to make less work. Now, before you leave, I want to ask this question. Sometimes in some math classes you might study division rules. So, suppose I did I to the 16,528. Of course, you could do the division on that one. But does anybody know how to look at 16,528 and know if it's divisible by 4? Yes, Aiden, what is the rule?
Well, I don't know the exact rule, but if there's a 20, 28 is divisible.
So you're saying because 28 is divisible by 4, it is divisible by 4? True. If you want to see if a number is divisible by 4, all you have to look at are the last 2 numbers. If the last 2 digits are divisible by 4, then it is divisible by 4. So we know because it's 28, the remainder would be 0. What if I did I to the 743? Is 43 divisible by 4? No, what's its remainder? 40 divided by 4 would be 10 with a remainder of 3. So it's I cubed, which is negative I. So if you don't want to do like full long division on some big numbers, you just divide the last 2 numbers. That will always work. Okay, your homework assignment is page 152. It looks like a lot of problems, but know that some of them are cycles of I, and some of them are adding and subtracting, so they're not going to take long. You do have a quiz tomorrow. So make sure you know end behavior and mathematical notation. That's with all the infinities. Make sure you can do, like I pointed out in your homework assignment from last night, number 67 and 70. Find a factor, find the other zeros, write complete factorization.